Yeah, very good afternoon to all of you. Today we're going to discuss about the overview of geospatial technology for hydrological modeling, its application in flood peak estimation and hazard vulnerability assessment. So first, let me tell you a brief idea. All of you must be aware about the hydrological cycle, but it's mandatory to start with that only. So hydrological cycle is nothing but the cyclic process. So how water vapor forms and condensation occurs, then rainfall processes will be there, then surface runoff processes will be there. So there are complex processes involved in integration to there are several forms of the steps or milestones of the hydrological cycle, like precipitation, snowmelt runoff, interception, soil moisture, evaporation, and runoff. So we have to, why we need to do the hydrological modeling? Just to quantify the different parameters in a very well manner to predict the runoff, and we'll talk about these things further. So let me tell you about the crisp of this lecture material. So basically the modeling has to be done because to predict the runoff quantity, and of course this has been done because of some reason. So here is the reason is the flood. So various causes are the floods are heavy rainfall, dam break, breaching of embankment, drainage congestion, storm surge, glacial lake outburst for flood, etc. So as we I have already know that in 2013 there was a disaster happened in the Kedarnath place. So this is the picture. The above one is the Rambara pre-flood of that event, and the picture of Rambara after the flood disaster. So the main question is that it is the natural hazard. So can we stop these hazards to become a disaster? Because there is a difference between the hazards and disaster. Hazard is nothing but the event, and event can be like any event, like drought, earthquake, landslide, flood, anything. Any event can be called as the disaster hazard. But when it comes with the vulnerable, it comes to the vulnerable area and the risk is involved, and then risk has taken place, then the integrated things we can call as a disaster. So the main thing is that can we stop these disaster, or we can predict these disaster, or we can manage or mitigate. So we can of course predict. We can't stop these disasters. We can predict and we can manage and mitigate, but the gap areas are like communication, real-time information. So extent of the hazards or damage happened, road connectivity, day-to-day monitoring, all alternative routes for the rescue and relief. These things can be very well planned. How to plan these things? So there is the answer to that query is the hydrological modeling. By the way of hydrological modeling, we can understand the hydrological processes involved in happening these hazards and these disasters. So hydrological modeling is nothing but it in the involvement of application of mathematical expressions that define quantitative relations between input and output. So input here is the flow forming factors like precipitation, snowfall, or glacial lake outburst flood, etc. And output is the flow characteristics, flow extent, and characteristics like velocity, depth, area, inundation area, etc. So the utility of hydrological modeling is why we need to do this: to understand the hydrological processes, to estimate the individual hydrological component, to generate scenarios with respect to land use changes and climate changes, to manage water resources for the benefit of mankind, river management, groundwater management, and of course to forecast the extreme events like flood and drought. So we can say that a hydrological model is a simplification of the real world system that aids in understanding, predicting, and managing the water resources. So but the main problem lies behind the hydrological modeling is the variations. We have India is a large country, and we have varied type of variation are there, like spatial variation. Rainfall occurs in western part of the country is about 120 mm per year to 12,000 mm per year. In the eastern part of the country, seasonal variations are there. Rainfalls, rainy season, the 4 months rainy season, 70 to 90% rainfall occurs in only that rainy season. Annual variations are there. Some years are drought years, some years are the wet year. So these type of variations we should take care before going for the any mitigation and other plans. So for to understand these variation effects on the flow characteristic and other things, we need to do the hydrological modeling. So how to choose a particular hydrological model? So there are certain type of hydrological models available. The first kind is the lumped model. Lumped model is the nothing but the lumping of the parameter it can do. So it doesn't account for the spatial distribution of input variables or parameters to represent the heterogeneity in vegetation, soils, or other watershed characteristics. So some parameters in a hydrological model can be lumped or some can be distributed. So lumped parameters means the watershed or the sub basin or a small catchment, if it represented by a single parameter of anything like vegetation, a single type, soil, a single type, or land use, a single type. So it can be called as a lumped parameter. And if lumped parameters are involved in any model, so it can be said as lumped hydrological model. Otherwise, it can be a distributed model where the parameters are the heterogeneous, and these models explicitly accounts for the spatial variability of input variables, typically by dividing the watershed into equally sized grid cell, and each grid size will have a different type of topographical characteristics and the thematic characteristics. So distributed model examples are like SWAT and HEC-HMS are the distributed model, and we can say that the Rusle revised universal soil loss equation is a lumped model. Or certain different type of models are also available, like empirical model and physical models. Empirical models are based on a simplified experimentally derived relations such as linear regressions, etc. So Rusle or SES curve number method, Rusle is an empirical method and SES curve number method is a physical model. That model derived from equations describing conservation of mass, momentum, or energy. And there are certain different other categories like event based model or continuous time scale model. So event based model, that means the model can take into account the event hydrological processes only. Like HEC-HMS is an event based model, and the SWAT model is a continuous time scale model, long time scale model. So there are different variety, there are hundreds of the hydrological models are available. So how to choose a particular model for a particular study? So there are some criteria I laid out for the selection of hydrological model. So these criteria are framed according to the categories like space discretization, if we want to choose the lumped model, semi-distributed model, or distributed model. In category of hydrological processes, this can be categorized as empirical approaches, conceptual, physical, or vegetation layer, single layer, two layer, multiple layers. Accordingly, soil layers also can be defined, but just we need to remember these things whenever we go for the lump behavior to the distributed behavior of the model, the complexity increases. So the third column represents the complexity rank, low, medium, and high. The model will become more complex when we go for the further distribution of the parameters. So these are the very well known models like HEC-HMS, SWAT, MIXI, and WIC. So the function of these models are more or less similar. Each model can take rainfall as an input and give output as this sediment, soil erosion, nutrient fluxes, overland flow, infiltration, annual yield, peak flow, and these are the generalized output. But the main difference is lies in the processes. Like HEC-HMS is the suitable only for the event based model, not for the long-term hydrological simulation, and SWAT is a long-term hydrological simulation model, continuous time scale. And snow process also can be represented in SWAT model, but HEC-HMS model, the SWAT the snow melt domain is not very well mature. However, like these two are free models. And if we talk about the WIC is the large grid size model. It has the capability to categorize the flow parameters in subgrid level. So subgrid variability and macro scale model it is, and the models are more or less Mike and C and WIC are physically based in terms of runoff, base flow, watershed scale. More or less, all of these things are similar, but the main difference is that Mike C is a commercial software. However, all the other three are freely available. Now, if I discuss about the SWAT model and HEC HMS model, which is very widely used all over the globe, and the input parameter preparation is not very tedious like Mike sheet. A lot of parameterization are there because it is fully distributed model, and it has different mathematical expressions for different parameters. So obviously the input parameter preparations are a bit complex. The same way WIC is also a bit complex model. SWAT and HEC HMS are freely available and compatible with the GIS also. HEC HMS is compatible with ArcGIS with the name of GeoHMS, and SWAT is with the name of ArcSWAT. So if we talk about the SWAT, SWAT is acronym for the Soil and Water Assessment Tool. It is a physically based river basin or watershed scale model. It was earlier developed to predict the impact of land management practices on water sediment in large watersheds with varying soil, land use, and management conditions. It is continuous evolved process to develop a model. So the SWAT is a combination of different models like GLEAMS, CREAMS, EPIC, HW, RRB. So it is an ongoing process. The each and every other process which is better in the other model, it is combined with the SWAT model, and it has been reached at a matured state now. It is designed to predict the impact of land use and management on water, sediment, and agricultural chemical yields in ungauged watersheds. And the main advantage is that the model breaks the entire catchment into sub-catchments, which are further divided into hydrological response unit. Hydrological response unit is nothing but the combination of unique land use, vegetation, and soil characteristics. So the HRU level, it does all the hydrological processes on the HRU level, so can give the more accurate results compared to the HEC HMS or other empirical or lumped models. It is semi-distributed, physically based, and process-based data-driven river basin model. As I said, it is a continuous time scale model that operates on a daily time step. If we want to go for the sub daily time step also, we can obviously go. There is an optional parameters are available. This is the public domain software, and it can be searched at SWAT Texas AMU website. The main utility of SWAT model is extensively watched in all hydrological field. Like SWAT model is used to run hydrological models to get water balance ratios like stream flow precipitation ratio, base flow total flow ratio, ET precipitation ratio, and other ratios it can give as a output results. And it provides maximum upland sediment yield also. There are several modules are also available in SWAT like reservoir modules, the snow melt runoff modules, and other modules. So it can be used in different ways, and quantifying the impacts from land use changes on the runoff and modeling the long-term impact of management practices also can be done. So if we talk about the data requirements, so the main input data set in terms of meteorological, so 5 parameters are required: daily rainfall data, maximum and minimum air temperature, solar radiation, relative humidity, and wind speed. Using this data, it is able to describe water and sediment circulation, vegetation growth, nutrient calculation based on the amount of precipitation, mean daily temperature rate. Snowfall also can be determined by using the degree day factors. So these are the meteorological data requirement. Other data sets, whatever required, I'll come to that. So this is the overall model framework. We have the input in one side, hydrological parameters, meteorological parameters, digital elevation model, and land use land cover maps. When these input parameters go to the SWAT model, the output can be generated as surface runoff, evapotranspiration, total flow, infiltration, and a lot of parameters it can give as an output. We talk about the simulation processes. So it has two modules of the to handle the processes: land phase of the hydrological models, hydrological cycle, and the routing phase of the hydrological cycle. So in land phase, what SWAT model does, it take care of the hydrological process, generate the grid based output like soil moisture, infiltration, and runoff or other flow characteristics. And in routing phase, it routes that generated runoff to the common outlet of the watershed, that is the single draining point. So calculation of runoff volume, how it does, basically it uses the SCS curve number method for the calculation of runoff. SCS curve number method is the formula, I can read it. Q is equal to P minus IA. IA is the initial abstraction. P is the rainfall whole square divided by P minus IA plus S. S is the surface retention, which is a function of curve number. So we can define S is equal to 25400 divided by curve number minus 254. If anybody doesn't know what is the curve number, so I can tell you curve number is the number which represents the runoff generation potential. So if the curve number is 100 for a particular surface, so the 100% of the rainfall can be converted into the runoff. So the potential of that surface is 100% for generation of the runoff. And so curve number, we can say that the curve number is a function of land use type, soil hydrological group, and AMC condition, antecedent moisture condition. If moisture is more, so runoff generation potential is more. If we replace IA initial abstraction is, we can assume that it is the 20% of the total surface tension. So the equation can be converted as Q is equal to P minus 0.2 S whole square divided by P plus 0.8 S. So that's how the SWAT usually calculates the runoff. There are several methods are also available, but this is a widely used method, SCS curve number method. And this is the graph showing the curve number. The precipitation is in the x-axis, direct runoff is in the y-axis. If you can see, the curve number is 100. So the amount of precipitation will be same as the amount of runoff. And AMC condition I was talking about. So these are the curve number which is written, which the graph is showing. It is only for the AMC 2 condition. So AMC, antecedent moisture condition, is nothing but it is the cumulative sum of the previous 5 days of the rainfall. So if it lies between the 12.5 to 27.5 for a particular reason, in dormant season, it will be a AMC 2. If the rainfall of previous 5 day, like AMC 5 day, exceeds or it will be below 12.5, so that it will be a AMC 1 condition and AMC 3 condition. So there are certain formulas available to convert the curve number values from AMC 2 to AMC 1 or to AMC 3. So this is the curve number table for the combination of the land use type and soil hydrological group. Now if we talk about the estimation of peak runoff. So peak runoff, there are certain direct methods, as we all know. Current meters, staff gauge, crash stage gauge is the direct method, direct measurement method, conventional method to know the peak runoff rate. However, the indirect method, like based on the equations, there are several methods like Manning's formula, SCS curve number method, Talbot's method, and rational method. So SWAT model generally used is the rational method to calculate the peak runoff rate. Here the peak runoff is a function of C is the runoff coefficient, I is the rainfall intensity, and A is the area of the watershed. So it can be said that the Q is a function of CIA. and the time of concentration it can calculate as a subdivision of the categorized way, like summation of the overland flow time of concentration plus channel time of concentration. So with the inclusion of overland flow time of concentration plus channel flow time of concentration, the rational method formula, the conventional rational method was uh, uh, modified as Q peak is equal to alpha TC, that is the inclusion of the time of concentration, Q, and area. One another approach, water balance approach, is also there. It is in the model of sweat water balance, where the Horton's equation is used to calculate the infiltration. So if the precipitation is less than the infiltration capacity of the soil, then there will not be any runoff. If precipitation is greater than the infiltration capacity of the soil or infiltration rate in the soil, so the difference will give you the runoff. So that's how it balances the water. And ET estimation also has been taken care by SWAT model by different methods: Penman-Montier method, Priestley-Taylor method, Hargreaves method. So it depends what method to be used depending on the what parameters are available with you. Input parameters are different for different methods. So in order to obtain accurate forecasting of water, nutrient, and sediment circulation, it is necessary to simulate hydrological cycle, which integrates overall water circulation in the catchment area. Hence, the model uses the following water balance equation in the catchment, where this surface water is the function of the base humidity, base retention, the base humidity, rainfall volume, surface runoff, seepage of the water from soil to underlying layers, evapotranspiration, groundwater runoff, etc. So this is all about the land phase of the hydrological processes. And if we come to the routing phase, so there are several options are available for the hydrological routing, like Muskingum routing method, variable storage method, and also SWAT uses the Manning's equation to define the rate and velocity of the flow. So this picture is giving the complete idea of the SWAT model project setup. Here in the left hand portion is showing as the input, land use, soil map plus digital elevation model are the topographical inputs or thematic inputs, we can say, in combination with the meteorological inputs. So these are all inputs required. Meteorological inputs, 5 parameter: wind direction, wind speed, relative humidity, solar radiation, maximum minimum temperature, and rainfall. These are the 5 meteorological parameters, along with the 3 things. One is the topography, that means digital elevation model, and thematic layers, land use maps, and soil map. These are all parameters required to set up a hydrological model, SWAT hydrological model. Then it converts it, process these parameters or these layers in a GIS platform. Watershed delineation will be done, HRU will be defined, then model simulation. There is also an option for calibration and sensitivity analysis in the model. Then finally, after the integration of the observed discharge data, model validation can be done, and finally output will be available in terms of infiltration, soil moisture, runoff, sediment, nutrient fluxes, etc., etc. Now, this is all about the SWAT model. If I talk about the HMS model, hydrological modeling software developed by HEC, Hydrological Engineering Center of USDA, I guess. So here also the input more or less are same: DEM, land use map, soil map. When it go to the GIS platform, hydro processing will be there. Generation of sub-watershed maps, CN grid data maps will be prepared, and hydrological processes will be defined. Then it will be exported from the GIS platform to the non-GIS platform. That means the HEC HMS. HEC GeoHMS is a compatible version just to prepare the input data set for the HEC HMS. HEC HMS is a standalone non-GIS version where we can set up the different models or different equations to be used. Then meteorological inputs will be there, and the output will be generated. Now, if I talk about what are the geospatial inputs we can provide, So obviously the topographical input elevation layer is required. So elevation layer means the digital elevation model, which can be easily obtained from the remote sensing image, and derivatives also can be prepared like slope, aspect, flow direction, flow accumulation, drain. Cover area, snow water equivalent. Why I am telling this the land surface parameters, because we can also assimilate these remote sensing derived parameter like soil moisture, snow water equivalent, snow cover area, evapotranspiration. We can also assimilate into the SWAT model to get my model better prepared for the forecasting. So these are the Indian imaging systems which help us to derive these parameters, and the resolution can be from 1 kilometer to 0.8 meter resolution. It can give you the global coverage, and application specific dataset is also available. Now, if we talk about the model selection, the equation or the model selection, so there are several options are available in HEC HMS and SWAT, both the models. Like loss method, there are several options: initial and constant method, HEC exponential method, SCS curve number method, Holtan's method, Green-Ant method. These are all options are there in the modeling software, so we can select any of these method for to set up the model. Surface runoff method includes unit hydrograph, Clark's hydrograph, Snyder's unit hydrograph, SCS method, kinematic wave method, excuse me, flood routing, Muskingum modified files, kinematic wave methods are available. So it depends the which method has to be chosen. It depends on the parameters available with you. Like the parameter required is written in the right side of the table. For initial and constant method, initial rainfall loss, constant loss, and impervious area is the crucial inputs. Other inputs are optional, but these are the mandatory inputs. Likewise, in HEC, exponential starting loss, initial accumulated rain loss, rate of change of loss, exponent of loss, impervious area. These are the required inputs. SCS curve number method needs only the land use map, hydrological soil group map, and curve number table. Holtan's method needs the equilibrium infiltration rate, growth index, available soil moisture, exponent of moisture storage, impervious area. Likewise, Green-Ant method needs the initial loss, volumetric soil moisture deficit, wetting front, suction. So these are all about the loss method. That means the how much water is getting lost into the surface by the way of infiltration or surface retention or detention and other things. So if we want to calculate the surface runoff, so there are several other methods: unit hydrograph, Clark's hydrograph, Snyder's, SCS curve number, and kinematic wave. So different parameters required are like hydrograph ordinates, time area curve, time of concentration, storage constant, time lag peak coefficient, SCS time lag runoff curve number, and in kinematic wave overland flow length, slope, runoff coefficient. Snyder's unit hydrograph, in this the parameters required are like length of main channel from the basin outlet, length of main channel to the point near to the centroidal, time of concentration, and the coefficients representing the basin slope and storage. So these things also can be easily available using the GIS software. Only the main input is required as digital elevation model to calculate these parameters. Like if we talk about the flood routing method, so Muskingum method needs the coefficient of storage, weighing factor, number of sub-reaches. Muskingum method needs the channel length and channel slope, and the same for the modified pulse method, which is easily available using the GIS. So RSGIS component, if I sum up the RSGIS component, how this RSGIS
can help you in setting up the model. So better to choose the SCS curve number method for the surface runoff estimation as well as for the loss method, because only the land use map, hydrological soil group map, and curve number grade is required for setting of the SCS curve number method, and these three can be easily available using the remote sensing image and the GIS software. Mosquito method, the length of channel and travel time can be derived using the remote sensing and GIS, geospatial technology. Now, I talk about the case study, so we have done several studies for water balance computation for different regions, different watershed, and other areas. If I show the entire Indian landmass, it will be good for the listeners. So this is the GTOPO 30 DM was used. So soil map of India derived from FAO's digital map of the world, and UMD land cover classification map of India we have used to set up the model. And this is the daily time series of estimated runoff base flow and ET average over entire India. This is the output generated by the hydrological model set it. This is the estimated hydrological component for the year 1995, 2000, and 2005. We have generated by the only the changing the land use map for three different years. So we can just see how the temporal changes are there in the hydrological components. And we have also estimated the runoff potential of the major basins of the India. So the CWC and we have whatever we have estimated more or less are same in terms of the runoff potential. So this type of studies can be done using the hydrological model, simple hydrological model. And if we talk about the at the time of disaster, what hydrological modeling can cater. So we can quickly set up any hydrological model for the site where the disaster happened or hazard happened, to just estimate the disaster, to assess the disaster, how much disaster has been taken place, what are the vulnerable areas, and how to take the preventive measures or the mitigation measures. So for Kedarnath disasters, the estimated we have estimated flood discharge during this one week after the flood season. So this is the picture showing the damage happened to the Rambada or Kedarnath temple. So this model was set up in the Hack HMS software in just 1 hour duration. Only the DM land use map and soil map were required, which was available with us. And this is how the output is generated. So the kinematic wave based runoff generation method we have chosen up along with the Muskingum routing method. So this is the maximum peak it is showing as the 600 around QMAC happened occurred in the afternoon of 16 June 2013. Now if we talk about the risk assessment, the another aspect to do the hydrological modeling, hazard, vulnerability, and risk assessment. So if we talk about the outline of the risk assessment, what is risk and how to assess it? So first we need to understand what is the hazard, what is the vulnerability, and what is the risk. Hazard is nothing but any event which leads to the disaster or not. It depends on where this event takes place. It is in the vulnerable area or not, and vulnerability defines the exposure of that system which is at risk. So the combining integrated effect we can say as the risk is equal to hazard multiplication multiplied by the vulnerability multiplied by the exposure. If we talk about the technical definition, so hazard is any substance, phenomenon, or situation which has the potential to cause disruption or damage to people, their property, their services, or the environment. It is the threat of a stress or perturbation to a system and what it values. Vulnerability is the concept which describes factors or constraints of an economic, social, physical, or geographic nature which reduce the ability to prepare for and cope with the impact of hazards. It represents the degree to which a person or a system or a unit is likely to experience harm due to exposure to perturbations or stresses. So we can categorize the vulnerabilities like hazard specific. So there are different hazards like drought, flood, landslide, earthquake. So hazard specific vulnerability can be defined, or setting specific. This is concerned with the prevailing socio-economic arrangements of the area. And the risk is the probability that negative consequences may arise when hazard interact with vulnerable areas, people, property, or environment. It is a concept which describes a potential set of consequences that may arise from a given set of circumstances. If this happen, then this will happen. Like this, it is a conditional probability and magnitude of harm attendant on exposure to a perturbation or stress. So we can say that the risk is a combination of interaction of hazard, exposure, and vulnerability, which can be represented by the three sides of the triangle. If any one of these sides increases, the area of triangle increases. Hence, the amount of risk also increases. If any one of the sides reduces, the risk reduces. If we can eliminate one side, then there is no risk. If you delete exposure of, or if you delete vulnerability of your, if you delete the hazard, so there will not be any risk. So how remote sensing can help to assess the hazard, vulnerability, and the risk. So the remote sensing data requirements for flood and cyclone disaster management. So a large swath image is shown at the left side. This is the pre-flood condition, and the right side of the image is showing the flood condition. So a large swath for the flood condition to observe at larger scale, a large swath image is required. Like we have used WIFS, wild field sensors data, where the swath is 810 kilometers and special resolution is 188 meter. So we can't see the damage in much detail, but we can see the extent of the damage happened. Then for the detailed studies, we can choose different resolution images like high temporal resolution and large swath, medium temporal resolution, large swath, low temporal resolution, limited swath, low temporal resolution, very limited swath. So whenever we go for the higher spatial resolution, so the temporal resolution might be less, and the location specific information we can get. So this can be said as the global to local method. And these are the list of sensors which we can use for the flood and cyclone disaster management studies or analysis of the damage happened. So WIFS, AWIFS, LIS3 or PAN. So you can see the resolution is getting decreased from 188 meters to 5.8 meters, and swath is also in comparison decreasing. Revisit frequency, if we talk about the revisit frequency, so this IIRS-1C, IIRS P4 resource set images, they more or less daily coverages are there. If we can combine the different data sets for from different sensors, so data availability is within few hours after acquisition. You can see in the red band, this is the pan image of the red band. Flood inundation area is appearing as the grayish nature. However, in infrared band, it is appearing as the dark. So this is the image. All weather. Yes, this is the IIRS data of the same day, 10 July 2002, when the weather is very cloudy, and we wanted to assess the damage happened due to the flood. But due to the clouds, the optical remote sensing images cannot capture the great details. So here the advantage of microwave SAR data can be taken up. So microwave data can be penetrated, the microwave bands, the cloud can be penetrated, and it has the all weather and all time capability to sense an area. For the case study, if I want to show, this is the pre-flood image of the Assam state. And this is the pre-flood river and water bodies of the Assam state. We have mapped the water body in a normal year. This is the radar set SAR image of the same area, and you can see the black patches shows the flood inundation area apart from the river area. So this flood map of the Assam state was prepared, and the monitoring of flood wave in Maregaon district, Assam state, if we track, then the optical images doesn't show this much detail of the flood affected area or the inundated area. So we have taken the radar set SAR image of June 2006, then AWIFS image shows the clouds over the affected area, then radar image of the 16 June, and so on. So this is how we can track the progress of the flood inundation area by using the different temporal images. Like for the Bihar floods in 2004, flood progression and recession we have tracked as viewed by the satellites. 20th Feb there was a normal things pre-flood image, then radar SAR image 27th June, 19th July, 21st July, and 29th of July. So how this flood wave progressed and how much area is getting inundated, and then recession limb also we have tracked. So there is a graph showing the how water level has rises and declines to its normal state, and the normal image was this closed flood image was the of 12th of August 2004. So this way we can have the idea about the flood inundation temporal progression maps. This is the same Bihar flood for year 2008. This is the image of April 2008. Then 20th of August 2008, you can see the breach location where the lake was breached. This is the 22 of August 2008. You can see the in the image of the 20th August 2008 where the breach occurred. Only this small part of this region is getting inundated, and it is getting progressed. In just 2 days time, it has progressed almost double in the area. Then this is 23rd. This is 27th of August. So in 7 days, in 1 week of this Kosi River, the turn of Kosi River getting straight. This 29th August, the whole of the area, this it can be seen as the flood inundation area in Madhepura, Sahara and Supaul districts. So this was the map prepared for different temporal progression of the image. This was the animation prepared out of these images only. So this is how we can assess the damage occurred, how the hazard turns into the damage. There are also a way apart from this, we can track the area over the Google Earth also. Like this is the Srinagar, Uttarkashi and upstream area, which is showing as the temporal images in 2004, 2010, 2017, March and April. So you can see how the river flow, how the water flow is getting progression. So here also we can map. If we don't have any access to the remote sensing SAR data or optical data, so we can use all always the Google Earth, which is the freely available data it can provide. We can just download the data and manually digitize the river network and map the inundation area by using the different temporal images. This is the Mandakini river basin up to Rudraprayag. And there is another method, hand tool. This is the height above nearest drainage. This tool uses the different if we have the layer of this river topography, river network, so we can assign the vulnerable area nearby the area depending on their height. Sorry. So that's why this method is called as the topography based flood prone areas identification using the height above nearest drainage. So the area near to the river is more vulnerable. The area or the location far from the river network is less vulnerable, but the height matters a lot. If the height difference is more, even the location is very near to the drainage network, but the height difference is more, so the area will be less vulnerable. So that's how we can assess the vulnerability of the area. When it comes to the flood damage assessment, so the same example I'll quote: generation of district-wise flood inundation statistics. We can generate the flood layers, and different statistics can be find out based on the number of pixels. When we got the flood inundation area, we can have the count of the flood inundation pixels multiplied by area, so it will give you the statistics of different how much of the area is getting inundated. And by integration of village layer and flood layer integration in the GIS, so we can identify which village or which area, which city is getting affected and the percentage of the effect. This is the Marigaon district in Assam state based on the analysis of radar set data of 13th of July 2004. So we have assessed that submerged crop area is around 30,388 hectare, and the crop area is shown in yellow color, and submerged crop area is shown as the red color, which is getting affected. So this type of district-wise flood damage statistics can be drawn using remote sensing and GIS images. This is the temporal statistics we have generated 20th July to 12th of August. How much area is getting inundated, number of village marooned, crop area submerged, and length of road road connectivity submerged in the water area. So the space inputs to the flood mapping, monitoring and modeling, which are the crucial inputs which can be obtained from the remote sensing, like digital elevation model, land use, land cover, pre and post disaster images are available. Snow cover time series maps can be obtained from AVIS or MODIS. SAR image tuning cloud cover, high resolution images, river cross section, precipitation, satellite communication, differential and normal GPS points for elevation, integration of remote sensing data in GIS, and use of GIS tools for watershed and river damage assessment. So this is how we can use the space-based inputs and geospatial technology to assess the damage. This is the for the Assam space technology for flood disaster management. The same thing, the historic flood of river Brahmaputra during September 1998, where it has caused a lot of damage in year 1998. So this was done, and apart from the data collection, data from the satellite space-based input we have taken generate useful information or using the GIS software. And finally, the most important thing is the dissemination of the information we have extracted using the space technology. So there is a saying that right tip to disaster management. What is the tip? Right time, right information to the right people. So this is all from my side. if anyone wants to discuss in detail or any project topics or any study, whatever you people are doing, you can directly mail me at arpit@irs.gov.in, and also keep visiting IRS YouTube channels, IRS ISRO Digital Content, EduSet IRS Dehradun. Thank you so much. If any question is there, I'm available to attend those.